Okay, so we're going to pursue what we did last time a little bit further. We have these two examples. We started with 2 times 3. We talked about an array of 2 by 3. We talked about factors of 6 being depicted this way. And we talked about another example of 3 by 5. We're going to up the ante a little bit now. So I'm going to grab some graph paper because that allows me not to have to draw messy squares. There. So this time, I'm going to begin with something that is going to be, just let me count this, 5, 12 tall. There's one line that's 12 tall. And I'm going to go 13 wide. That should be 12 by 13. I may have made an error, so I'll get you guys to just count it and make sure that I'm okay. It's not quite a square, hopefully. One. I think I need to shorten it if I want it to be 12 tall. Would you agree? Okay, so there's our box. Now, what kind of facts would this give us? This would give us a 12 by 13 array. This would give us a rectangle with an area equal to 12, oh, that's so messy, by 13, right? And this also should give us 12 rows of 13 and 13 columns of 12. We could figure that out, and I want you to watch how that would go. Let's just go 12, we could count them. 12 times 13, I want you to watch how these numbers happen. 3 times 2 is 6, 3 times 1 is 3. But then when we make the new one, the 10 is going to multiply by the 12. That's why we put the 0 here, but we don't always talk about that. 1 times 2 is 2, 1 times 1 is 1, and then we add 6 and 5 and 1, and we know it's 156, or we use a calculator, right? But what if this rectangle could help us do that? I am going to get us to split this in some interesting ways. I'm going to go 10 and 3 and 10 and 2. And when I do that, that allows me to drag this down and make quadrants, much like we did in that last video when we added to the 6. And when I make those quadrants, I think you can tell me very easily how many squares are in each one of those spaces. So, bye-bye, Liam. The first one is here, okay? And in this one right here, how many squares are in that space? Do you both know just off the top of your head because you know that it's 10 by 10? Yeah. So I'll ask you, Adnan, to tell me how many are in this box and write it in there. And Ariana, you can write in this box to tell me how many are in that one. Thank you. Super good. And we recognize this one from the previous day, right? The previous lesson. And there we have 120, 56. 156. Let's notice where everything is from those two ways of thinking. The 36 is here because that was where the 2 times 3 happened and the 2 times 10 happened. And the 120 is here because that was where the 10 times 2 happened and the 10 times 10 happened. So we have another way of thinking about this. And what we know in good research is that we can use this idea to multiply in a small way. This takes less space, right? We don't have to have graph paper. But we could do it like so. We could say, I'm going to take my 10 plus 3. I'm going to take my 10 plus 2, and I'm going to use this little grid, or yeah, it's called a grid, to multiply those things in those different directions, and then add them up to get 156. So I'd like you to give me a happy face if that example makes sense. Okay. Ariana, you too? Okay. So just to be clear, we have these traditional ways of talking about the array, the area, the multiplication. We can draw it and we can grid multiply it. So this opens up kind of a new world of how to multiply. And if we multiply in this way, we can use this way to factor as well. So I'll give you an example of something quite similar. And I'm going to introduce you to some shapes. I've got this x square shape. And I've got this, I'm going to call it an x shape. And these are also x shapes, but they're going in the other direction. And I've got some unit shapes. And I'm going to have 6 of those. So if this were a question from 10C, for example, and occasionally I ask a question like this in my 9 class, it would be, we have this thing called an x squared piece. It's x by x in dimension. Let's actually call it that. I've got 5 x's, and I've got 6 1s. How could I arrange those things in a very nice rectangle where the distributive property holds? And this game we're about to play, when I say the distributive property holds, that means that there are no t-intersections. I'm going to describe that in a second. So t-intersections means I can't do something like this. I can't place 2 of these up against this because that's a t-intersection. If you're beginning to drive, you drive down here and you crash, okay? All of the avenues have to go all the way through, okay? All the streets and avenues. So I'm going to just try this. I'm going to place these 3 along here because I kind of know that 3 times 2 is 6. And I have to make a space that will really help my 1s go into place. And then I'm going to put these guys in. I made my verticals a bit skinny, but I think that'll be okay. And do you see how that goes together? I want to make a grid of this because if I make the grid, you may notice how similar it is to the question that we just did. If I have an x squared in this part of the grid and 3 x's in this part of the grid and 2 x's in this part of the grid and 6 x's in the bottom quadrant, I can count 1 x length, 1, 2, 3 unit lengths, and I can know that one of the factors is x plus 3. Can you tell me what one of the factors this way is going to be? This is kind of like an area question, right? Go ahead, Ariana. Yeah, it's absolutely x plus 2. Okay, let's check, because when we were here, and I made this grid, I could take the numbers here and they multiplied to the number that they, like this row and this column intersected here to make the 100. 3 times 10 was 30. 2 times 10 is 20. 2 times 3 is 6. You saw how that worked? So here, is it true? X times x is x squared. X times 3 is 3x. X times 2 is 2x. And 3 times 2 is 6. This adds up to the 5, right? So by arranging pieces into a rectangle, much like we've done in this example and in the previous recording, we can factor. We can factor polynomials by arranging them into a rectangle. That's a big deal. That tells us a lot of things. Now, before we leave this example, because this example we can take in a couple of ways, before we leave it, I want to just check something. What if x were 10? Like, what if this was a function? And I know you guys are in grade 11, so what if this is a function? What if we have y is equal to x squared plus 5x plus 6? And we make a little table of values. And we say, well, what if x is 10? Well, x squared will become 100. X times 10 will become 30. Three times 10 will become 30. 2 times 10 will become 20. There's our 5 times 10. And then 3 times 2 will become 6, just a 6 at the end. So there's the 100, there's the 50, and there's the 6, 156. So what we see is this example right here is really related. In fact, it's a point on the graph of this thing. If we were to go to our calculators right now and write in y1, and we wrote the function x squared plus 5x plus 6, you would scroll down to x equals 10 and you'd see 156. These are related ideas, okay? Okay, we're going to end this recording and pick up in the next recording. So I'm going to ask that we go to our next recording, Ariana and Adnan, and I'll just stop here.